recording now? You guys not talking to the microphone?
Yo.
Yeah.
Yo, 1, 2.
And everybody needs to think about questions to ask substitutes.
I will ask you still even up, Amanda.
Okay.
Of course.
Okay, we're rolling?
Yep.
Alright. Good morning, everybody. My name is Wael.
And I'm Anthony Troxell.
We are B-Scale. We are on the B-Scale project.
Alright, so first we're going to talk about why we're doing the B-Scale project and why it's concerned to the university. So there's been a decline in wild pollinator populations, which is bees, across the United States. And we depend on bees for our food and for other plants that support the environment in our area. And then I'm really tired, hold on. So the kinds of information that the entomology department, which is the group that asked us to work on this project, is looking for is individual bee behavior, and specifically the kind of individual bee behavior that leads to successful colonies and unsuccessful colonies. Alright, so what is the B-scale? So the B-scale is going to be within a closed test environment. They're going to try to grow a live colony within a test structure and keep track of bees' daily lives. And then the way that it's set up is that there'll be tube sections for entrance and exits for the bees so they can go out into the wild and also go into a food area that they have supplied for the bees. The entomology department has supplied for the bees. And okay. No, we're fine. Alright. So let's talk a little bit more about the bees. Yeah. Alright. So these are our wild foraging friends, the bees. And right here is a bee that's actually been out foraging. This is a ball of pollen that is collected on the hairs on its back leg, and it can also collect nectar on the inside. And so the bee scale is actually going to be used to figure out how much of this pollen and nectar bee has gathered during a foraging trip, or if they've even collected any at all, if they've just gone out for a stroll. And then we have a sizing image there so you can see these little nuggets, how big they actually are compared to a nickel. Pretty small. And the bees themselves can weigh anywhere from 61 milligrams to 264 milligrams, and the pollen loads that they carry can be from 0.6 milligrams up to about 30 milligrams. Let's see.
Alright, so the system that we're working with will... So the system that we're working with will consist of a load cell, a PSOC 5, a PSOC 4 BLE, and a ADS 1262 ADC, which we will get into further discussion about. So the component details. So our main component is the load cell, which is the heart of our measurements. and we're going to be working with a strain gauge. And what that does is it measures the strain as the change in resistance happens. So if you look to the right, there's a Wheatstone bridge that is that shows the mechanism of it. And as there's resistance on one side, the other side does an opposing resistance, and it outputs opposite polarities of voltages on each side since it's bridged. So that will give you the voltage that we output to our to the rest of our device. We are going to be working with the ADC as well, which is also a big portion of our device, and we're going to be working with the 32-bit delta sigma. We chose this because it's preferable, because the higher the bit count, the less quantization noise that we will have, and converting the analog signal to digital signal will help us process it when we do things such as filtering and enter this data to our PSOC. So for prototyping, we're starting with our 100-gram load cell, which is mounted on our board. It's a shear force load cell, which means it uses it reads with the forces, two forces opposing each other. We have the color-coded wires that show reference voltage, ground, the positive output, and the negative output that will be outputted to our the rest of our system. And the red wire, the reference voltage, is excited by 3 to 10 volts, and it has a resolution of 600 microvolts per volt output. And yeah. So we hope to lead on to the optimal S256 load cell, which is a lot better than our prototyping one. And it's also a shear force load cell. It's capable of measuring a lot better with its resolution, as it can go down to the 1 milligram resolution safely. And since, like Anthony stated, that the bees range around that area to like around 50 milligrams, and that will be ideal for our scale implementation. It'll be good for the environment in the tube, and it has an excitation of about the same voltage, and it does 1 millivolt per volt, so it'll give us better readings.
What was the previous one?
Can you go back?
The output, just go back. There's 1 microvolt.
Yeah. So this is a nice drawing that we found that kind of shows the mechanism that we just talked about. As you apply pressure, you see that the straining occurs, and as it bends as well, you see in the Wheatstone bridge how it affects the resistance. All right. So more on the ADC. Like I said, we're using a delta sigma ADC, and what it does is it takes a 1-bit stream and it oversamples it as it does the delta sigma modulation.
What does it mean it takes a 1-bit stream?
So when it goes through the modulator, it goes through like a 1-bit.
Okay, after the modulator.
Yeah, and then like I said earlier, we use a 32-bit ADC, which helps with the quantization noise as we convert our signal from an analog to digital signal.
Okay, so some of the complications we faced when making this test setup was we have a lot of wires for our current setup. That causes a lot of inductance, as well as we're using quite a bit of proto board, which means a lot more parasitic capacitance, and a lot of misconnections and thermal noise from the resistors. Additionally, our power supply isn't as stable as we'd like it to be, which causes excitation voltage across the load cell to be a bit noisy, which means our signal's also slightly noisy. To deal with flicker noise, we're not quite sampling near DC, but not very high frequency, so it's not as bad as you'd really expect it to be. Thermal noise is across all those resistors that we have just to set up our amplifiers. Our quantization noise is handled just with that really powerful A to D. White noise isn't, well, it's not so much a big issue, it's just we haven't seen the issue yet in our testing. Our voltage signals are extremely low at 10
10 microvolts to 100 microvolts after amplification. And our noise is at the 100 nanovolt to about 10 microvolts range, which can show the challenges in this project. Okay, so this is just a picture of our test setup being fed a sine wave onto the PSOC 5's amplifier setup, just bypassing the load cell to show that the entire setup works without the load cell. Okay, so you can see in the top left our PSOC 4 dev kit. In future, we'll replace it with the PSOC 4 BLE, but for now, we're using the PSOC 4 dev kit just to transmit data to our computer so we can read with MATLAB for miscellaneous data. Our PSOC 5 is doing all the heavy lifting using an instrumentation amplifier, which isn't actually pictured there, as well as it's feeding data into...
You're using the instrumentation amplifier of the PSOC 5?
We made one. We made one.
In PSOC 5?
Yes.
Can you talk about that? It's good?
Yes.
Not good.
Could be better.
It could be better.
That one is to be so low noise that you probably do want to go to external specific designed instrumentation amplifier and then go into the PGAs of the ADC as soon as possible. So that if you instrumentation amplifier should get right at the load cell.
All right. So that instrumentation amplifier is actually being fed into the filter, but in this picture, that filter was very heavily attenuating the signal, and we're no longer using it, thankfully, because of all those inductors. And then finally, that signal is sent to the AD, which will process our signal.
Is it not sufficient to go into the PGA stages of the ADS 1262?
It actually ends up...
Look at that. Look at